Hello students, let us start the lab class. Today's experiment is on flip-flops. So this is experiment number 6 and we will be working with the 4 flip-flops, namely T, D, SR and JK. There is a brief theory. Even though you are familiar with the flip-flops, let us have a brief recap. A flip-flop or latch is a circuit that has two stable states and can be used to store state information, just like a bistable multi-vibrator. This word bistable multi-vibrator was an older word. Now we do not use it. We use only latches and flip-flops. The circuit can be made to change state by signals applied to one or more control inputs and will have one or two outputs. Flip-flops and latches are fundamental building blocks of digital electronic systems used in computers, communication systems, etc. Now you can see this SR flip-flop truth table, and if it is S and R, set and reset. If set and reset are 0, 0, there is no change, and whatever was the previous output, that will remain the same. If set is 1 and if reset is 0, then output will be 1, or if set is X or 0, let us say reset is 1, then output is 0. So reset means output will become 0, set means output will become 1, and if both are 0, then the previous output will remain, but if both are 1, now that is the illegal state in SR flip-flop. But in JK flip-flop, that is going to be overcome. You can see the JK flip-flops truth table here. If J and K are 0, 0, no change. If J is 0, K is 1, then that is reset. If J is 1 and K is 0, then that is set. And if J, K both are 1, then output will toggle. So here the name JK basically means it is named after the famous scientist Jack Kilby. But it doesn't mean that Jack Kilby invented this flip-flop. Okay. It simply means that the flip-flop is named after the famous scientist called Jack Kilby. He was the one who made the first VCO on a single chip, voltage controlled oscillator on a single chip, and that was an integrated circuit at that time, and that was quite an achievement at that time. So this flip-flop is named after Jack Kilby. And you can see the last state where both J and K are 1, 1. There it is not an illegal state or indeterminate state. Their output will toggle. So next we have, as per the clock now, clock rising edge and falling edge. Next we have the D flip-flop. When clock's rising edge is there, the next Q state will become D. That means if D is 0, after the rising edge of the clock, Q will become 0. Similarly, if D is 1, Q will become 1. If there is no rising edge of the clock, then Q will remain as it is. So D is generally called as delay here. Means the value at D will appear at Q after the rising edge of the clock. So it is also called as a delay flip-flop. Lastly, T or toggle flip-flop. There is a separate control input called T, and if T is 0, then Q and Qn plus 1, next state, both are 0. As long as T is 0, and if there is no clock, then output will remain as it is. When T is enabled, that means when T is 1 and when clock is applied, the output will toggle. It will become 0, will become 1, or 1 will become 0. So that's how this is called as a toggle flip-flop or T flip-flop. All these flip-flops find their use in many electronic hardware circuits, such as in counters, in registers, in sequential circuits where decisions have to be made. So now let us see the program for the flip-flop. First, we will be dealing with the SR flip-flop. Let me discuss the Vhdl program. Library IEEE, use IEEE standard logic 1164.all, entity srff underscore is port, clock and reset are input ports, and we can declare S and R together as one vector, 2-bit vector, input standard logic vector 1 down to 0. And we can declare outputs as Q and Q bar. We can declare them as buffer here in Vhdl because we will require them both at LHS and RHS now. So in Vhdl we have this particular option of giving it as a buffer. Now let us see the architecture. In this architecture, begin process clock SR reset. You can see the sensitivity list where when there's a change in clock, when there's a change in SR, when there's a change in reset, this block will be executed. So if reset is 1, Q is assigned to 0, Q bar is assigned to 1. Else if rising edge of the clock, then case SR. When SR is 0, 0, Q is assigned to Q, Q bar is assigned to Q bar. When 0, 1, Q is assigned to 0, Q bar assigned to 1. When 1, 0, Q is assigned to 1, Q bar assigned to 0. And when 1, 1, Q is assigned to X and Q bar is assigned to X because it is a indeterminate state. And when others, it is null. End case, end if is corresponding to this if reset, and end process and end architecture. This is with Vhdl. This is the test bench code for Vhdl. Let us see Verilog program. Module srff and inputs are again SR is a 2-bit vector, then reset and clock are single bit, Q and Q bar are all outputs and it is registered here. Always at passage clock begin if reset is 1. You can see the equality operator here. If reset is 1, Q has to be assigned to 0, Q bar has to be assigned to 1. Because there are two statements here, we are enclosing them in between begin and end. If reset is not 1, then we use case statement. If SR is 0, 0, Q is assigned to Q, Q bar is assigned to Q bar. As there are two sentences here, two assignments here, we should again enclose them in between begin and end. This is required in Verilog. Now if SR is 0, 1, Q is 0, Q bar is 1. Else if SR is 1, 0, Q is 1, Q bar is 0. And if SR is 1, 1, then it is a unknown state. Default Q is 0, Q bar is 1. End case, end module. Now this is the Verilog code for SR flip-flop. Let me stop sharing this lab manual and let me share the Xilinx ISE. So you can see this Xilinx ISE window here. I have already copied the SR flip-flops code into this editor and the test bench is also there. This is the SR flip-flop Verilog code. In the test bench, I want to show you something. You can see the test bench here where I have added one block called always here, always begin, #20, clock is not of clock and end. In general, when we work with Vhdl automatically when it creates a test bench, it will create a clock also. But whenever we work with the combination circuits, we have to keep on deleting that clock segment. Verilog will not define any clock. We have to define the clock when it is required. So that way, in the Verilog test bench, we are defining a clock. Every 20 nanoseconds, clock will become not of clock. That way we have defined as of now. Now, in the initial block, I have given the values for SR. Reset is 1 first, then after 100 nanoseconds, reset will become 0. Then I am giving SR as 0, 0, then 0, 1 and 1, 0 and 1, 1. We are giving the time 100 nanoseconds and here 80 nanoseconds, simply like that. There is no specific reason for this. Now this is the test bench and this is the Verilog code for SR flip-flop. So first let me check syntax the code of the SR flip-flop. Next, let us check the test bench. Now let us simulate behavioral model. So you can see the output here. Let me bring the cursor here. You can see initially when S and R are 0, 0, now reset is 0. When reset was 0, Q and Q bar were X. Now when reset is made 1, Q became 0, Q bar became 1. But now when reset is again becoming 0, you can see at the bottom there is this clock, because we have defined clock in the test bench. When SR is 0, 0, then when SR is 0, 1, then when SR is 1, 0, you can see when S is 1, Q has become 1 and Q bar has become 0. Lastly, when SR is 1, 1, both are, okay, sorry. Oh, sorry, I have to share. Oh, yeah, this is coming in a different window, so I have to share. So let me do one thing, let me share the screen directly. Okay, now I have shared the screen. I hope now you can see. So let me explain again. Here when initially when reset is 0, Q and Q bar are undefined. Later on when we make reset 1, that is when exactly Q will become 0, Q bar will become 1. And then later on reset has become again 1. And you can see accordingly for 0, 0, 0, 1. And then for 1, 0, you can see Q has become 1, Q bar has become 0. Lastly, when S and R are 1, 1, Q and Q bar both are unknown values. And whenever the simulator shows the unknown values, it will show the red color. And whenever it is high impedance, it will show the brown color. So now both are unknown. Now this is the output for SR flip-flop. Let me come back to Xilinx. Let me come to implementation and let us see the Rtl schematic now. You can see this Rtl schematics block where S and R are 2-bit, clock is 1, reset is 1, output is Q and Q bar. When I double click on this, you can see it has a logic here. This is an AND gate and you have an inverter here. So AND gate with inverter is NAND gate. Now in the RTL, as it is not having NAND gate, it randomly picks up whatever is available in the library. And in general, FPGAs work on AND gate, OR gate and inverters. Because ultimately inside FPGA, there are only multiplexers. There are not even gates. And gates are also implemented using multiplexers only. That is why you can see one AND gate and an inverter here. You can see one more inverter, one more buffer also here. But you can see these two blocks here, where it is showing FDRE, FDSE, one for Q and one for Q bar. And you can see the same line reset is coming here. It is reset to this flip-flop and it is coming to this flip-flop. Now you may wonder, we have declared only one SR flip-flop. Why are we having two blocks here? The reason is, inside the Xilinx library, by default, a flip-flop is declared as one library element. I'll zoom in and show it to you here. So you can see here now, this is a flip-flop which is by default declared already in the library. Now this is basically a D flip-flop. And it has got a chip enable. You can see the CE, it's a chip enable. This C is a clock here now. Then it has got a reset pin here. And output is Q. And as we have not declared the hardware of the flip-flop here, we are going for a behavioral description of the flip-flop. But as such in the library, already the flip-flop is available. So it has understood, the synthesis tool has understood that this is a flip-flop, and accordingly, it has taken two instances of the flip-flop. Why has it taken two instances of the flip-flop? Because we want one for Q and one for Q bar. Now, accordingly, for that S and R logic, it has implemented this particular circuit along with this circuit, along with this inverter, along with the NAND gate. It has applied it to the respective flip-flops as per the truth table. So this is the Rtl schematic. Let us see the technology schematic. In the technology schematic also, in the beginning, you can see only this single block diagram. Now, when you double click on that, now you will see in the technology schematic some more things. You can again see a flip-flop here, and you can see one LUT here. You can see one more flip-flop here. Now, this flip-flop is same as I showed you earlier. Even in the technology schematic, as it is already containing the flip-flop as a library element, D flip-flop as a library element. It is picking up the same thing from the library. But it has applied some logic in the technology schematic here. We have one buffer here, then we have one LUT here. What is there inside this LUT? Inside the LUT, there is one OR gate. And then we have one more flip-flop here. Now, one is, this is corresponding to Q, and the other one is corresponding to Q bar. You can see here, it has applied one inverter here, so this is corresponding to Q bar, and this is corresponding to Q. So even in the technology schematic, you can see LUT along with that the library element flip-flop itself. Okay, what is the question? If there is already a flip-flop present, is it necessary to code for the design of a flip-flop? Yes, we should. We should write the code for the flip-flop because we may use these flip-flops as part of a counter or a register or any other sequential circuit. Now, it is the freedom of the synthesis tool to pick up the respective library elements, right? As we have seen in our earlier lab experiments also, we will not tell the synthesis tool what to do. Ultimately, we want the relationship between inputs and outputs to be satisfied, that's all. How the synthesis tool implements this is not of our concern. Okay, but we should write a code for the flip-flop because it is our requirement. Now the tool may pick up whatever is available in its own library. Now the tool is smart enough to directly pick up the flip-flop. You just understand this point. Otherwise, the tool would have constructed again cross-coupled NAND gates, and it would have applied all those logic sequences. And in the technology schematic, we were supposed to see the complete circuit diagram, isn't it? But we did not see that. The reason is the synthesis tool automatically understood that this is a sequential circuit. In the sequential circuit, when there is a rising edge of the clock, all these events are happening, which means this is definitely a flip-flop which is available with me. That is how the synthesis tool has understood, and it has created the schematic here using the library element flip-flop. The reason why in the library flip-flop is present by default, the reason is flip-flop is a normally usable electronic block in all our electronic hardware, right? So each time when we write a code for flip-flop, by default, it need not generate other circuits for it using the gate primitives. As such, a flip-flop can be stored in the library and it can be accessed anytime by the synthesis tool. Because ultimately, whenever we synthesize a large project written in Vhdl or Verilog, it will end up in what? It will end up in combinational, sequential, combinational, sequential, combinational, sequential. It will happen that way. Because in the combination logic, decisions are taken. But in the sequential logic, it is the storage which happens and comparison with the previous state happens. So both are necessary. As far as our electronic hardware is concerned, decision making and storage, both are necessary. So when it is necessary, flip-flops are basic elements in our hardware. So when when they developed the synthesis tool, they came to know that flip-flop as a basic element is required in the library. That's all. So that is the reason we have this flip-flop. But for your question, the answer is you will not be knowing what all elements are present inside the library for the synthesis tool to access, isn't it? You will not be knowing. So you will have to write the code for a given flip-flop. It is up to the synthesis tool to choose whatever is available in the library and connect it together. That is the idea. Now this point will become clearer to you when I simulate and synthesize the other flip-flops, because then also you can see the synthesis tool will pick up the same flip-flop again and again and again. Only thing is logics will change. For SR and for JK and for D and for T, only the logics will change. Other things will remain as it is. Okay, that is the answer. Now let me close these things and let me come back to lab manual. You can see in the test bench code, this clock definition is there. This also you can change. It is up to you to choose the clock's time duration. Here we have chosen 20 nanoseconds. And the same stimulus which I have applied. This is the output which I showed. And then this is the Rtl schematic which I showed. Now let us go to JK flip-flop. Vhdl program. I'll go a little faster because it is the same Vhdl program. Only thing is, you can see here, rising edge clock, if JK is 00, 01, 10, when JK is 11, you can see Q is not of Q and Q bar is not of Q bar. Only in that case, toggling will happen. Otherwise, everything is same as SR flip-flop. And this is the test bench code in Vhdl. Clock definition is not there in Vhdl because it is not required in the Vhdl test bench. Automatically, the clock definition also comes into picture. Now coming to Verilog code, it is the same program, Verilog JK and input JK, input reset clock, output reg Q bar. Only this last state, when JK is 11, Q is not of Q, Q bar is not of Q bar. And end module test bench is same here. And this is the simulation output and this is the Rtl schematic. Now let me copy this code into our simulator. File name, let it be the same, it does not matter for us. So let me save it and let me check syntax. I have to remove this test bench now because in the test bench the module name will be different. So let me check syntax. Now let us add new source Verilog test fixture. Let me write it as jk underscore test.v. So it has created a test bench, but the point is, as clock is missing, I should add the clock program here now. So let me take this clock program and I have added it here. And finally, I should add stimulus here. Okay, let me not worry about the indentation. Otherwise, also it is going to work. So let me check syntax, the test bench. So finally, let us simulate. Let me close the previous window. Now you can see the output here, where you can see here, initially when reset is 0, Q and Q bar are unknown. Then when reset becomes 1, both are, Q is 0, Q bar is 1. That is when the flip-flop is reset. Then when the reset is remaining 0 continuously. So when JK is 0, 0, it is the previous state. When JK is 0, 1, output is 0, Q is 0. When JK is 1, 0, J has become 1, so Q has become 1, Q bar has become 0. Later on, when it is 1, 1, you can see continuously it is toggling. Every rising edge of the clock, there's a toggle happening. You can observe that. Every rising edge of the clock, there's a toggling happening. So this is how JK flip-flop is there. Now let me synthesize. So synthesis is done. You can see the JK flip-flop block. When I double click, you can see a slightly bigger circuit now. Again, you can see this flip-flop here, one more flip-flop here, but you can see multiplexers here. There is one mux here, one more mux here, one more mux here, one more mux here, and you can see some logic here. There is one AND gate, one inverter. So this is how Rtl schematic is there. With the 3 multiplexers, 4 multiplexers, and 2 flip-flops which are present already in the library. Let us see the technology schematic now. Now this is the technology schematic. Let me zoom out. Now here you can see one flip-flop here, one LUT here, one more LUT here, and single flip-flop is being utilized for both cases. You can see now Q and Q bar. Now it has understood that this Q and Q bar are connected together because there is no unknown state here now. So the synthesis tool has understood that why should I take 2 flip-flops from my library? I can optimize my design. But what to take where? That way I will put LUT. So you can see one LUT 3 inside which it has got a circuit now. Similarly, inside LUT 2, it has got an OR gate now. So there is a buffer here and there is one more buffer below. So in this way, the synthesis tool has understood that using a single flip-flop, it can implement the whole of the code. Ultimately, this single D flip-flop itself is working like a JK now, because in this D, let me zoom in. You can see there is this chip enable, there is this D, then there is this clock. Now the chip enable itself, it is utilizing along with one OR gate, and it is using it as part of the circuit also now, part of the logic. And here in LUT 3, you can see this circuit. What is this now? A bar B, and let us say this is B, then C bar B, they are clubbed together. So it has connected it to the respective instances here, respective inputs here. You can see it has taken the output of Q also back to the LUT here. Accordingly, it has applied some logic, and using this logic, it has implemented the JK flip-flop. Now, this is the ingenuity or the brilliancy of the synthesis tool. Okay, now let me show you the next code. We have already seen the simulation output. The next code is D flip-flop. D stands for delay. So entity DFF, port D, reset clock, inputs Q, Q bar, buffer, and D flip-flop entity, architecture, process D reset clock begin. If reset is 1, then Q is 0, Q bar is assigned to 1. You can see, else if rising edge of the clock, then Q is assigned to D, Q bar is assigned to not D, and if and end process. You can see the way in which assignment operator is there in Vhdl. Now this is the stimulus. Let us see the Verilog program. Module, DFF, and then inputs D reset and clock, output registers Q and Q bar. Then always at passage clock begin. If reset is 1, then Q is 0, Q bar is 1. Else D is assigned to Q and not of D is assigned to Q bar, and end module. Now we have to define the clock in the test bench and we have to define stimulus. This is the output. Now let me copy this code. This is the code for D flip-flop. Let me save it and let me check syntax. Sorry, I have to remove this test bench. So you can see there is an error. Let me see what is the error. Line 1. Oh, here a space is required. Let me check once again. I hope now it is all right. Let me check it again. Yeah, now it is checked. Let us apply a test bench. So we have to define clock here. Actually, it does not affect even if I declare this always here also. Why? Because the whole program is concurrent, right? Right from module till end module, it is concurrent. In between, we are making it sequential. Even if I put this clock below also, it does not matter. But as we are following the sequence there, we are putting it there. Anyway, let me exchange it in the code and let me show you. So here I have applied the stimuli. Now let me take this always block and let me put it here. Still it will work. Why? Because the whole code is as such concurrent. So it will work. So let me check syntax, the test bench. And now let me simulate. So now you can see initially when reset is 0, output is in red color, unknown. Later on, now here, later on from the rising edge of the clock. Why this has happened here? Because in the code you can see, always at passage clock is there. See? Which means now reset became synchronous. This particular D flip-flop is now having reset as a synchronous input. This code refers that way. If you don't want this, then this passage clock and comma reset you should give. Right now, as we have given only passage clock, we have not given the reset in the sensitivity list. That is why output is coming this way. Later on, I will show you the changes also. You can see here now. Now reset became synchronous. You can see when clock is going high. Let me zoom in. See, before also reset was 0 here. D was 0, but there was no clock happening. So until then, it was XX. Now in the rising edge of the clock, it is changing now. So let me zoom out. So now, again, as per the rising edge of the clock, because we have told in the code that it is always at the positive edge of the clock. Until the positive edge of the clock occurs, output was unknown. Now output has changed to the green color. Now reset became 1, then reset became 0. When reset became 1, anyhow output is 0 here. Now you can see later on. Let me zoom out. Sorry. So you can see the output here now. In every rising edge of the clock, you can see the output is changing. Here you can see. Here you can see we have given the stimulus before the rising edge of the clock. You can see D has gone high here. Resistors have gone low here. But it is taking decision at the rising edge of the clock only. So there, because D is 1, Q is 1 now. Again, in the next rising edge of the clock, D became 0. So Q became 0. Again here, during the negative edge of the clock, D has become 1. But during the positive edge of the clock, Q has become 1. That is why it is called as a delay flip-flop. But here in this particular case, when D became 0, it has become 0 in the positive edge of the clock. That depends on how we give the stimulus inside the test bench. So we can give varieties of stimuli in the test bench, taking all these delays into consideration. So everywhere you can see Q follows D after the rising edge of the clock. Here also you can see. Now D has become low in the negative edge of the clock. But in the positive edge of the clock, Q has become low. Q bar has become high. So in this way, it is D flip-flop. Let me close this. And now, just for the sake of curiosity, let me put reset here. I have put always at passage of clock and I have put reset also. Now let me save this. Let us check syntax. And simulate once again. Let us see what will be the difference. Now you can see the difference. Earlier we had that unknown state. Now you can see there is no unknown state here because in the sensitivity list we put reset also, not just positive edge of the clock. So now the code is sensitive to the changes in reset also. That is how you can see the unknown state is not there. Otherwise everything else is same. Okay, when reset goes 1 and again when reset goes 0, later on you can see everything happening as it is. This output I had shown you earlier also. It's the same thing. Only difference is in the sensitivity list we added reset. So now it became a asynchronous D flip-flop. Reset is no more dependent on positive edge of the clock. Okay, this way we can have multiple types of designs in combination with reset and clock. Now let me synthesize. Synthesis failed. Is showing some error. Line 1 empty module DFF. Line 4 no support for Synthesis, mixed edge and level triggers, correct. You can see this now. When I put this passage clock and reset together, the synthesis tool is not supporting. Simulator is supporting. Synthesis tool is not supporting. So it is not so easy to make one asynchronous D flip-flop that way. We have to think of some other logic there. That's what it's saying. We cannot mix edge triggering and level triggering. You can see here positive edge clock, comma, reset, both are there. Reset is level triggering, this is edge triggering. So in the same always block, we cannot mix both of them. So you can understand, even though check syntax is all right, synthesis tool is not supporting. So let us synthesize once again. This is the Rtl schematic. Next, we will see the Rtl schematics internal block. Here you can see separately for Q and separately for Q bar, it has taken two instances of the same library element which is available inside, and it has put one inverter here. That's all, because it has understood that this is how the logic is working. So individually for true and complementary outputs, it has produced two instances. Let us see the technology schematic. Now in the technology schematic, you can see one buffer and then here one more inverter. It has put again two instances of these, and at the output of one instance, it has connected one inverter. So that has made it as Q bar, otherwise it is Q. There is no other logic. You can observe here. Even in the Rtl schematic, we saw one inverter extra. In the technology schematic, we are seeing only buffers extra along with the inverter. There is no other logic. So let me close this, and then the last design for today. We have already seen the simulation output of D flip-flop. The last design for today is T flip-flop. And in Vhdl program, you can see, I'll discuss only the process here. Process T reset clock begin. If reset is 1, then Q is assigned to 0, Q bar is assigned to 1. Else if rising edge of the clock, then if T is 1, then Q is assigned to not of Q, Q bar is assigned to not of Q bar. Don't get confused with this assignment operator in Vhdl with that of Verilog. They are different. Their context is different and their meaning is different. That's why I told you should observe the operator which is in Vhdl. In Verilog it will be different. Let us come to Verilog. Module TFF, input T reset clock, output range Q and Q bar, always at passage clock, begin. If reset is 1, Q is 0, Q bar is 1. Else if T is 1, then Q is assigned to not of Q, Q bar is assigned to not of Q bar, and end module. So let me copy this code into our editor. Let me save it. Now I have to remove the old test bench. Let me check syntax. Error. Yeah, there should be a space here after passage. So let me check again. Okay, let me add test bench now. So this is the test bench where we have to add clock and we have to add stimuli. So let me add clock. As you already know, we can add this always block anywhere because the whole program is concurrent. Only thing is we should not put it inside the procedural blocks. So this is the stimulus. Let me do indentation here also for the sake of beauty. That's all. Otherwise, it has no other role. So let me check syntax, the test bench. And then let me simulate. You can see here now, when reset is 0, I have shown you the other earlier problem there. We can club reset and clock together inside the sensitivity list, but simulator will support. Synthesizer will not support later on because it becomes a mixed type. That is why I have retained it now as it is. I will not change it also later on. Now T is 0 here. Now reset is also 0. That is why Q is X there. Now when reset became 1, Q became 0. Now here you can see when T became 1, reset remains 0 later on. When T became 1, in the next rising edge of the clock, Q has toggled. But T has remained 1. So again, output has toggled. But here T has become 0. When T has become 0, no change in the output. When T becomes 1, every rising edge of the clock, you can see the toggling happening. That means T flip-flop can be used as a divide by 2 counter now, right? As long as T is 1, Q will toggle for every rising edge of the clock. So the frequency of Q from now on, from this point onwards, frequency of Q is half that of frequency of clock, which means the output waveform became divided by 2 waveform of clock. We can use this T flip-flop as a divide by 2 counter also whenever required. So this is the simulation output. Let me show you synthesis output. When I double click on the RTL block, you will see again 2 flip-flops, but you will see this inverter coming back here and this inverter coming back here. You can see this output coming back through an inverter. So the synthesis tool has understood that toggling should happen based on the input signal T. That T is here. You can see that T here. That T is here. Reset is here. Clock is here. And the T is connected to chip enable here. And Q has come back to D by means of an inverter. So the synthesis tool has understood that toggling should happen means it is applying 2 inverters here. Otherwise, it's a default D flip-flop that is available in the library. Let us see the technology schematic. Now, in the technology schematic, you can see there's a buffer there and there is one inverter there. There's a single flip-flop here. And there are other buffers here. You can see from the output it has taken an inverter and that inverted output is going back to D, but it is taking that output here with one buffer and the inverted output it is taking with one more. So this is Q and this is Q bar. I'll zoom in and you will see that. See, this is Q, which is directly coming from output, and this is Q bar, which is coming from the inverted output. And it has intelligently put that inverter back here. And in the Rtl schematic, we saw two flip-flop elements, but here we are seeing a single flip-flop element, but with buffers and inverter. So the technology schematic is more intelligent than the Rtl schematic, because in the technology schematic it goes deeper into the optimization of the hardware. So in this way, we have seen the synthesis output of flip-flop, and we have already seen the simulation. That is the end of today's lab class. If you have any questions, you can still ask me, or else I'll stop sharing the screen and I'll stop recording also. Meeting will be on. You can write today's observation book and you can upload it into the Google Class. If you have any questions, you can ask me.
How do we decide the physical size of this?
How do we? I am unable to hear. Be a little more louder. How do we
decide the physical size of these circuits?
Like we will not decide the physical size of the circuit here, because we are now dependent on FPGA, right? So when we write a code, it will be implemented with the library elements that are available in FPGA. That's all. We will not worry about the physical size, because inside FPGA there are fixed library elements such as multiplexers and LUTs. So the synthesis tool will synthesize according to the components available in the library. It will create a netlist. Based on that, output will be provided to us. That's all. As far as the FPGA's usage is concerned, we as designers will not worry about the internal implementation. We are only interested in giving the input to the FPGA and taking the respective output from the FPGA. That's all. So the area or the size are not important for us. Reason is we have already paid to the FPGA, right? FPGA is a readily manufactured chip. As we have paid to FPGA, whether we reduce size or increase size, it doesn't matter at all. But in the next semester, you are going to work with Asic Design. In Asic Design, you have to take care about the area or the size there, because in Asic the size matters. Because in Asic Design, you are going to design a specific chip. There you should decide what was the total area of the chip and what was the size of each and every element inside the chip, because it is going to cost you a lot. If larger the chip, it will cost you more. So there we really work out on the size of the chip, and that is where you are going to involve yourself in making a layout for the circuit diagram. Here in FPGA design, we are not worried about making the layout. We are only worried about writing the code and then implementing it using FPGA. But in Asic Design, not just writing the code. Later on, you'll have to make a physical design also, or you have to make a layout for the circuit which you are trying out, especially in analog designs. Again, in digital designs, synthesis will happen there also, but that synthesis tool is much more brilliant than the present synthesis tool. There is a synthesis tool in Cadence which is much more refined than the synthesis tool of FPGA. FPGA uses LUTs and multiplexers, whereas Cadence synthesizer directly uses the primitive library elements, including logic gates, which are present in the Cadence library. You will learn more about it only in next semester. So as of now, understand that we are not worried about the physical size of the circuit here, because we have already paid for the chip. That's all. I hope the answer is clear to you.
Yes, sir.
Okay, any other questions? Okay, if there are no other questions, I'll stop recording.